approaches for autonomous driving assistance and AI data-driven engineering in automotive. And feel free to ask any questions or anything that you think can help you as well in the future. I will start with a small introduction on what we see today. So we see a big focus in changing the automotive industry from, let's say, mechanical-driven industry to electrical and software-driven industry. This is something that we see. We see a big focus on autonomous vehicles and autonomous assistance system like ADAS. Where we see various companies, various industries that they are trying to add either various type of sensors, starting from image sensors, LiDAR, radar, sound, and additional sensors that will come up in the next 2-3 years. Let's call it non-standard sensors. In the same time, we see a rise of look from this perspective. I don't know your figures, but this is what we see typically, that the data collection volume of a single test car for an hour long is around 50 terabytes. And if you put that into a perspective, if you have a specific number of cars into your ADAS fleet, you can reach around 10 petabytes on a single project, for example. And you have to understand that this is the raw data. So therefore, we have to then bring this into a data center, try to do kind of defeaturing, or if you want, you do, for example, subsampling, so, and then you do labeling and so on and so forth, right? And if you look on the right side, how many hours you need for 1 hour of testing drive to capture and tag that, that's really demanding task. It's one aspect I want you to just to frame some couple of issues here. And then if you look on the autonomous vehicles, autonomous driving assistance, we see those two things here in the car: the perception, sensor fusion, motion control, scene understanding, mission trajectory planning, and so on and so forth. And then we have the backend where you do have to test the data, and you have to secure those algorithms when they go out into FPGAs or GPUs in the cars. You need to do the training, the tagging, labeling. You need to do simulations and approvals before to send these things into the cars. And we see as well right now a big focus on bringing into the fusion, sensor fusion as well, and decisions, the real-time data like weather, traffic patterns, accidents, and so on and so forth. So all these things, they are kind of AI and data-centric system engineering for automotive industry right now, in the transition from mechanical focus to electrical and software focus into the future. This is something we call it a future-proof vehicle 4.0 platform for ADAS and autonomous vehicle, where we see it's not just a single vendor, it's just that the car of the future, you still need to work with your existing OEM suppliers, applications, third-party applications to host all these things into the vehicle. And then to connect those platforms together. Either they are sending their location, they are sending the battery capacity, and so on and so forth to the manufacturer like yourself, with the help of a cloud provider or a GSM or mobile provider. And then you have this vehicle control center, security operation center. Whenever let's say a car will be able to detect that there is a security breach into the system, which is becoming a very important piece as we put more software that will control the car and the engine in the future, until the OEM parties where they can come with their own specific platforms for particular things. I just give you an example. For example, you can have a small board computer that the OEM provider can offer the cloud platform that can control, let's say, over-the-air updates and so on. So that can be considered like that. So we see some challenges as we are trying to work with our customers and partners in this direction. First of all, how you handle this massive ingestion of the data, how you know exactly what video you should select for a specific edge case, the quality of the data, how you can synchronize, label, tag, and so on and so forth. And then how you develop, let's say, solutions that they are very robust and you can push them from on-prem or from your data centers where you develop them to the edge, so to the cars. And those things are as well reflecting to the way we develop software. So like continuous integration, DevOps things, which are melting down right now with the AI part. Last 3-4 years, we had only, let's say, the data scientists focusing on building the models to detect objects, to do semantic segmentation, and so on and so forth. But in the moment you want to put that in the production, you need to really use the existing software engineers and practices and involve in that. So it's a mix of all these things together. So we see this part moving forward into a complex ecosystem that is relying on 3 things: collaboration, accessibility, and auditability or traceability. So that is for audit purposes. And for example, here we're working with Volkswagen Group in Germany, with Valeo, Bosch, with Continental, ZF, NVIDIA, and so on and so forth, either as technology providers, either as tier 1 to suppliers, data centers. We try to understand as well the legal implications and so on and so forth, industry standards, and how those are reflecting to the technical side. And as you can see here, in terms of the development, it needs various steps here, starting from acquisition of the data until the test and connectivity-based validation. And all these things, you need to have open standards that you need to embrace. You need to have a hybrid approach. You cannot process everything on-prem. It's impossible. So therefore, you need to have kind of hybrid solution, collecting the data into the cloud, moving them on your data centers and forth and back. And obviously, everything has to be based on an engineering lifecycle management, we call ELM. And this is part of any kind of modern solution moving forward. So for autonomous driving engagements, if you consider development and testing and operation, you have all those 4 areas like service and technology research assets. So probably if you have Hyundai Research, they actually handle these kind of things for you. So they create the models, they can create, let's say, the optimization of those models for particular solutions you decide to put in the car. They did, for example, the pruning and so on and so forth. Then you have the automotive software engineering. So they have those teams looking for those things and integrating various hardware parts inside. And then you have the data management. And this is a very important topic because it's not only collecting the data, is as well, trying to, do the downsampling of the data sometimes from the videos, try to understand the metadata around that. If you have LiDAR data as well, how you can fit this together and so on and so forth. In terms of operation, you have the service technology research assets as well from the research. So whatever research is giving you, say, okay, this is good for further development product and so on. You need to incorporate that into your development pipeline. And then you have the vehicle operation center and security operation center that as you push more connected cars, as you push more this kind of software and over-the-air updates into your system, in your cars, then you need to have those vehicle operation center as well. If you look from the autonomous driving assistance in the future, like many in the loop things that you can take over, and how this will reflect the insurance companies that will handle the insurance from the car owner to the car manufacturer. So therefore, this is another topic that you need to take into consideration. And then obviously the connected platform, how you can bring this together via kind of form of cloud or on-prem solution, and how you collect all this kind of data and so on and so forth. So the part of autonomous vehicles is actually data, neural networks, and computation. You need to have these things when you push them into the car and understand how you can automate the things around here. So in a big picture, you need to understand your data, you need to have the best models for doing the inference, doing the prediction, and then you need to have the proper computational power into the cars to really drive this kind of technology. Here are some challenges you may know more than me, as maybe you are involved in autonomous driving assistance. So, for example, we have various traffic signs. For example, US, there are different traffic signs rather on highway compared with traffic signs in Germany. The same thing happened with small objects, weather conditions, all these things, sharp distortion. You need to deal with them when you train those algorithms. And therefore, you need to have a very strict way of, first of all, managing your data per region and so on and so forth. Sometimes you need to apply. Okay, I will continue. And sometimes you need to apply as well things like augmentation if you don't have enough science for a particular region, and there may be try to deal with algorithms. Is that sorry? Is that a question?
Okay. Florin, one second. Audience, please, go on mute if you are not presenting. Please go on mute. Florin, please go ahead.
Okay. Other kind of technical challenges in the real-time objection is the light reflection, distance estimation to the object. For example, whenever you want to have the autopilot, and obviously the bad weather condition, reflection of the light, and obviously typically you don't, depending on your strategy, we see companies that they rely only on cameras, as well as companies that they have a combination between cameras and LiDAR or radar and so on and so forth. So based on all these things, you always try to understand, how you fit your algorithms to take the best decision based on the sensor data that they're going to be fitted. And therefore, those are some of the challenges that we see there. And depending on the strategy of the company, that's something that they have to deal with this. And ask yourself, when you have everything, let's say, corrected and everything is working, let's say, until level 3 autonomous driving, what's happening when you see a corner case? How do you trace back that issue, and you find the data set that you need to enhance the models, and then you retrain and do the validation, and then you push back into the car over there or whatever the new algorithm, right? How long that thing can take. And that's one of the problems, because whenever you push something in the car, you always try to improve that thing, that software. It's not like putting a physical engine and changing the parts on the engine. It's quite difficult. On the software side, you can really push always more and more over the updates. So from AI perspective, we need a model life cycle, right? So we have to understand always a new data coming, the integrity of the data, the quality, the tools that we use them, and then try to see, how we can create new models, how we can validate them, test and deploy them, how we can have the approvals inside of the company for the models that they should be validated. We see companies that they are training in parallel at thousands of models in parallel, and they choose the best model. Or we see companies that they search for the best hyperparameters over months, or they try to do the monitoring of those models in the test fleet, and then try to come back and improve them. So therefore, it's a continuous process as we are driven by the data right now. To really push the best models out there, which means that we need a culture in the company, you need the proper technology that can really automate these things. We have to avoid things which are statically created. So the way we do predictions in your data center, probably you do batch AI. So you have systems, you start the batch process, workload manager across multiple of systems, GPUs or FPGAs for training, and then you get some results, and then you retrain and so on and so forth. As you are moving to the car, you're in online or real-time AI, real-time inference, and therefore the constraints are different there, because you have to concentrate more on latency, on the response message, what you do with that, how you orchestrate various, let's say, machine learning and deep learning models, and how you can really deploy them successfully in a very small power footprint that can be an embedded GPU, an FPGA, or a specific ASIC. So those are two different streams, which typically they were disconnected. And this is an AI workflow, how we see it typically, right? So we see companies like you collecting to the partners or directly a lot of data, and then you prepare those data sets. You do some sampling, you select whatever you need, you do labeling and so on, and then you start the training, finding the best hyperparameters, and you see here the time needed. But when you run inference, this is happening in seconds. But what's interesting right now is that you have this new data coming from inference, and we see companies in automotive space that they have more metadata today than the data itself, and that is a challenge. So the metadata, if you push this in the future in your cars, will grow faster than the data that you can collect. So it's an imperative thing to really collect these things from the cars as a new metadata to improve future things into the car, not only for algorithms, but can be as well for the way the cars will be built, the way the engines will be built, and so on and so forth. So that's very, very important. It's like having your entire, let's say, production for 1 year, and you have all the people which are driving this production, and they will come back with feedback on all the aspects, and it's giving you this feedback, and then you need to decide what to do with it. Try to imagine that you can have that flow continuously coming to you, right? And that's another challenge that we see that have to be solved. So last couple of years, we're concentrating on this kind of architecture. So we had some accelerated infrastructure in data centers, data lakes. We build data stores based on various technologies. You see here Hadoop, file system, NoSQL, parallel file system, and so on and so forth. Then we did distributed computing to do distributed training. We started using TensorFlow, Kafka, PyTorch, and so on, and build the APIs that will, it was able to offer us the microservices that we need. For example, simulation. We want to simulate a road, for example, with Carla, and we wanted to have those APIs from an inference side. So this is what we have seen so far. But as we push more on the edge part, we see this is actually splitting. And we see the action and decision separated right now. And one of the important things is the governance AI, right? So how you are sure that whatever you train and has the right data inside the model, it's robust enough and is giving you something that is completely, let's say, predictable in the time on the same kind of roads and so on and so forth. On the edge side, we see a tendency right now of federated learning, something that IBM Research was working for the last couple of years to bring more innovation there. Local cache from the sensor data, because you need to have some traceability of what's going on there, and in case something happens, you need to debug that. So the question is how you can bring this together, right, and have something consistent. This is a multi-tenant self-service accelerated platform that we see typically in data centers, which is based on servers for management. We call it control plane, and we can consider this is Red Hat OpenShift or Kubernetes based workload managers. We need to have something like dedicated systems for training and dedicated systems for inference. First of all, from the cost perspective. Second, you may have for inference FPGAs, and therefore you may want to choose the inference to run on the FPGAs to test that into data center before to test it on the fleet. And on top of this, we have an initiative with Red Hat of the Open Data Hub, where we want to come up with things like Kubeflow, internal Git for internal collaboration between the research, development, and other teams. Adversarial robustness toolbox here, trusted AI part, which is IBM has open sourced and delivered to a Linux Foundation a couple of weeks ago. Things like deep search, product from IBM Research, all the machine learning and frameworks and libraries, we call it WMLCE, what's machine and computer edition. So anything like PyTorch, I will speak about it in a while, but all those frameworks packaged together, available for those platforms, based on optimization, which is another important thing when you are trying to do, for example, simulations or try to find the best hyperparameters. This is something that can help a lot, especially, for example, I was mentioning the data-driven engineering when you do, for example, CAD design and then you do simulations. So Bayesian optimization can really help in that direction. And then Anaconda Team Edition, we know that those systems are hidden from internet, are internal research organization, they don't have internet access and so on. Therefore, all the Python packages can be mirrored there locally, so any kind of researcher or developer can really just do a kind of conda, install all the packages without any issues. And these channels can be curated based on the company, let's say, policy, security policies. And if you look on the computational goal, typically when you build a model, you need just a workstation, right? So when you create a new architecture, and so you don't need something very big. When you try to do continuous integration and you try to validate that model with real-time data and so on, you start having a need of more computing power. And this is just an example of how many GPUs you may need, how many systems, how much time can take from an hour to weeks, days, and so on and so forth. And all these things are really interesting because if you try to really bring, for example, the build of the model, continuous integration, train model, or real-time and optimization into a single platform, you can serve them with the hardware. But from the software perspective, you need to reconsider the way you actually create these things and serve all the people working on these various streams. So Kubeflow, we have seen successful implementation of Kubeflow. We have even a customer, it's Continental, using Kubeflow in the production today, where they really create those AI pipelines, not only for training and for inference, but as well for finding the hyperparameters. For example, with Catlib, which is a great tool to really create those clusters and empower people with the web interface requesting whatever they need. and do their own experiments. And this is based on a multi-tenant self-server accelerated platform, so you can have various departments, just using the same cluster for various things on different namespaces. So that's a very important thing. In terms of distributed deep learning, you can use, for example, either Horvath or you can use Spark to scale. So there are advantages and disadvantages for each one of them. Into a bigger picture, here is the open data architecture, where you can see that everything sits on top of the OpenShift. And then we have various things that you can install. So the ODH is like a meta operator, right? So from there you can install Kubeflow or any kind of Jupyter Hub, or you can create your own operators to install all these things. And if you look from the software perspective, you can even create something like, can have Jenkins CI/CD, for example, and integrate that into existing AI pipelines. So you can create not only for training and validation, but as well you can create further things like how you can push further into a software stack based on the latest code that has been merged into a Git, pushed into the Jenkins, and has been built a specific software, included into a container, and so on and so forth. So all these things can be bringing this thing that we call it Open Data Hub architecture, which is a vision based on the Red Hat OpenShift. Now, regarding on-prem hardware capabilities, so what we do, we partner with IBM Research on various parts. This is an example for the computer vision. So we take from the IBM Research technology, for example, to accelerate the GLMs on the GPUs with things like SnapML. We use, for example, things like how we can enhance some models, how we can run models that they need more GPU memory, right? So they're big enough, and therefore the memory in the GPU will be taken by the model, and we have less space for the data. And they created this large model support for PyTorch and TensorFlow that can extend the GPU, the model running out of the GPU to the system main memory. And auto hyperparameter optimization, elastic distributed training you see here, until the way we see future inference processors. So a lot of things going on here. This is a next generation AI hardware that IBM Research is working currently. We published in Nature as well some information about the new inference core we created. And there is a roadmap. This is published information. You can search through IBM on the way we see the moving from digital AI cores to analog AI cores with optimized materials in the future. And the first step has been made was this summer, where we actually released this processor, we call it in-memory computing, using rest-in-memory device, where we can do inference. And the beauty of this is that if the chip has no power, the weights are still remaining there. That's a very important thing compared with a traditional chip when you don't have any power and you power down the system. You still need to load the weights, so the trained models, into the chip memory. And that's something which is very unique here. And IBM Research is trying to partner with various suppliers. And therefore, if you'll be interested in moving forward, you are free to contact us in this direction. In terms of systems, we have 3 pillars. One is for data acquisition. We call it big data workloads, so, like Hadoop file systems and so on, where you bring all this data together. Then we have the training systems like IBM AC922 systems. Like a majority of the large systems in the world, they use this piece of the hardware. It has a unique advantage, which is the link between the CPU and the GPU. It's NVLink. And that bandwidth is allowing you to do large model support or to process more data for demanding models or for, let's say, high resolution images. So that's an advantage of this system. As long as you do, for example, like kind of machine learning things and you have small models, yeah, it's the same like on any x86 system, which is out there. And as we're discussing about inference and simulation on-prem, we have this system called IC922 that is delivering the up to 6 NVIDIA T4 GPUs, and you can add as well FPGAs if you want, like U50 into the system. And therefore, is a single strategy, very simple when you try to do all these things into a data center. In terms of storage, we have this ESS 3000 based on Spectrum Scale Storage, where we're trying to really focus on what's needed. So a platform that can really drive either object storage, either can have integration with OpenShift. So whenever you deploy containers, you can create persistent volumes, you can retrain them, you can create snapshots, and so on and so forth. You can scale this across multiple systems, communities, in a single global namespace. It's like having for example, the system there, having another one, for example, in Germany, for example, and then you see the same data, and where the data is created will remain there, but you see it globally and can be moved everywhere needed. And then obviously the integration with the Spectrum Discovery for metadata management, so classification, metadata tagging, high volume index, auto tagging zones, where the data has been created, in what kind of fleet, or for example, if you are searching for particular time frame or data which has been collected on a various, let's say, roads in various conditions, how do you select that today, right? So all these things are somehow melted together into this Spectrum storage, which is certified to run with IC922, and NVIDIA DGX systems. So we have customers using both of them, and it's really, it's a great system. And this is an example of how the system look like. It's just 2U as well, so you can put those units as much as you want. It's an NVMe-based storage, which is driving up to 768 gigabytes memory per controller, and you can really equip this with various NVMe flash drives, as you can see here. So it's really a very powerful system that we can connect via InfiniBand or 100 gigabit Ethernet, and the goal is to have everything modular, not only from the computing perspective when you add another server, and so on, but as well we wanted to have at the storage level. So here you see some example here on some tests we have done with 3 storage units to serve NVIDIA DGX1 servers. So you can see the performance throughput, just going almost at 100% by adding another box for the same file system. And that's very powerful, and that's very granular when you try to go and implement this. You don't have to buy from the beginning something big to serve something that you expect in the future. In terms of the software stack, I was mentioning the AI Fairness 360, Adversarial Robustness Toolbox. Those are available on the Git as well on the Anaconda channel. Can be installed. Then we have something like Watson Studio Code, Community Edition, Visual Insights, Inspector, all this software stack, or workload manager like Spectrum LSF. When you have a larger cluster and you do batch AI, you need to manage multiple people working on the same cluster, who's taking the GPUs for how long, and queues, and all these things. Until all this kind of cloud pack for data, for enterprise, driverless AI, for auto ML, and so on and so forth. So we have a lot of software to move in that direction. I will concentrate now on 2 things. One is the Power AI vision for labeling and annotation. And then I will just present the WMLCE, some of the capabilities we have in innovation, and some use cases from the automotive industry. Right, so you see here on autonomous driving assistance, we have a couple of things: classification, detection, some segmentation, path planning, and Power AI Vision can really offer us like a web interface. So we wanted to have a platform that can really scale seamless and give people only access to either to APIs or to web interface for do the labeling, do the augmentation, do training, train some models, export those models, do the quantization, and so on. So we come up with this thing. This product has 2 years on the market right now, where it's really scaling on top of Kubernetes. Everything is just give him a cluster, and as you add FPGAs or GPUs, you can now automatically use them. You don't have to take care on, where your model will run, how long, and so on and so forth. So for example, for annotation, in this case, is object detection, how you do it, right? So typically we have an image, and in that image, we need to have something like to refer to an XML file and have the position of the object in the image. This is one example of implementation. In this case, you give access to the people which are doing the annotation to a web interface and say, okay, you can create objects, so they can go and create some pedestrians, bicycle, whatever they want. They can load either images into the platform via API or via the web interface, or they can load videos. And then they can take from the videos, they can take the frames at, let's say, 1 second, 2 seconds, 3 seconds, depending how much they want. And it's just an example of how that can look like, right? So then you click on the image and say, okay, now I want to label those objects here. And you can do currently box and polygons, but we're going to add freestyling as well. So you can have various options. You can zoom in if you want. You can go on the right side, add more objects if you need. You can, if you have objects which are one close to each other, you can hide objects. You can change the color and so on and so forth. So you can do all these things very fast. And it's very handy to do labeling and annotation with this thing. In addition, from the video, this is an example of the video where you just load the video and then you say, okay, capture frames. So the way we do it is that we can capture manual frames, or we can capture automated frames at a X interval of seconds. And we do here, you see here, I was mentioning that you can hide these things. So you can go on A6 and you can say, okay, I want to hide this object because I want to do a better labeling and annotation and so on, compare with what is out there. And then you can select all the images. We have as well semi-automated labels, which means that we prefer to train a model, or we can upload a model that we trained, and then we can use the platform to extract the labels automatically based on that trained model. And that is really helpful, especially when you're trying to, label hundreds of hours, right? So in the moment you have a model that will be, let's say, 86% or maybe 90%, you can use that for label extraction, and then you just go and correct or approve or delete what the system has identified as label from new videos. This can be done as well. While you're training, we give some information as well to the people, so they have the things like precision, recall, IOU, accuracy, all these things, you get them from the system. So at any time you can stop the training, and even you can retrain or put more labels or change the hyperparameters that the system can take into the training model. There's as well something that we offer for advanced users, like confusion matrix, PR curve, loss versus iteration. So this for more advanced users, where they can see where are the issues in their data sets, for example, versus the model that they want to use, and then try to improve that. Okay, in this case, okay, I have problems because I don't have scooters. I have I don't have nothing, obviously. I have a problem there, probably the same thing with the bicycle, buses, and so on and so forth. So we give all these things visually. You don't have to look for the CLI. And this is a multi-tenant platform, so people, they can collaborate here. And this is an example when you train your model and say, okay, I want to validate that model somehow. And then you just give new videos feeds that you have, and then you see, what the model will detect, what is the error in that case. You can select the confidence threshold, could be 99%, and so on. So all these things can help people which are doing this annotation on the platform and try to validate as well some model or detect corner cases. Another thing is the action detection that the platform can be done. So you can load videos, and then you can annotate from a specific second to another second a specific human action, right? And this is interesting because whenever you want to deploy in cockpit AI and you're thinking, okay, how I will just pass the responsibility from the car back to the human, for example, you may need to understand what's going on in the car, right? So this is just an example how this can be done. And then the system will actually learn those actions and to detect them. Another thing is the augmentation. The platform can offer as well some augmentation techniques, as you can see here. So blurring, sharpness, cropping, noise, and you can really play the brightness and contrast. That in case, for some use cases, especially for the common case where we don't have enough data, and just try to imagine a car that has a door open, right? How many such situations do we have in journey into a data set? Not that many. So that can help improve in that particular category and balance more the data set. Another thing is how we export those data sets. And so I was mentioning that we have this web portal where you can export those models, you can export the data sets, and you can further improve them. And at the same time, those APIs will offer you integration with either you want to start a training, you want to upload a new data set, all these things can be integrated as well at the API level. So whatever you can do on the web, you can do on the API level. So that will be easy to be integrated from this particular perspective. All right, so Watson Machine Learning Community Edition. So what we have done, it was like, whenever we want to go in the enterprise and then have some particular support, not only for TensorFlow or for PyTorch, but you want to have support, for example, for let's say NumPy or for any kind of thing, it's very hard. So majority of people, they use PIP. So we created this WMLCE, which it's freely available. You can find it on the Docker Hub. You can find it as well on the Conda channel for x86 or PowerPC, where we collect all these packages, TensorFlow, TensorRT, basically if you want to compile additional things, let's say on the latest Git, for example, PyTorch, Apex version of PyTorch, SnapML is innovation from IBM Research that can accelerate, for example, decision tree, so all these GLMs on the GPUs, and is supporting this model, either local operation on a single system, MPI or Spark. We integrated Dask, XGBoost, as you can see here. And as I was mentioning, this part of moving from on-prem to, let's say, edge devices, typically you need to have a standard when you do that, if you do quantization and pruning, for example. So we included Open Neural Network Exchange in support in TensorFlow, PyTorch, and Caffe. So that support is existing. You can train and can export that. Then we have the Spectrum MPI. So this is an IBM product for multi-passage interface when try to do distributed learning. We have our own library like Horvath. We call it distributed learning, but we see more adoption of Horvath when you try to scale at scale. Therefore, we included as well Horvath there. So we have the whole support in the package. And one additional thing is that when you get the system with GPUs today, you need to, and you compile all the stuff, you need to be sure that you have the right CUDA version, you have the right nickel drivers, Cudian drivers, Cudian software at the right version. And the question is, when you have a new version coming up, you need to create another virtual environment, how you deal with that, right? So always there's a dependency where, you go to a system and say, hey, just install this stuff for me, otherwise I cannot compile the latest TensorFlow. Because I don't know what kind of bug. So what we have done is that whenever you try to, for example, do a Conda install Power AI after you add our channel from the Conda, all the CUDA toolkit, CUDA runtime, nickel drivers, Cudian drivers that will be automatically added to your virtual environment. And therefore, we preserve the dependency. So therefore, you can go on a newer version or lower version. So that's very easy. So therefore, the administrators will have to just maintain the GPU driver, that's it, on the system. So they have to be sure that the system has the latest GPU driver. And therefore, this is something we done just for the packaging perspective, to push this very, very easy for the users and give them freedom in action. And it's available for bare metal or for containers. If you put the inference in perspective, we as well package the TensorFlow serving server, TensorRT, and Onyx, as I was mentioning. Now, a couple of innovations here, probably you have seen them so far from IBM. So the large model support, which is for TensorFlow and for PyTorch. For PyTorch, it's just one line to enable large model support. And we have seen some good performance improvements in training. Distributed deep learning as well, snap machine learning for GLMs, mostly for machine learning, where we accelerate these things which are, scikit-learn, for example, which is non-GPU accelerated. We can accelerate with our own library on the GPUs, and therefore, obviously, it's much faster to train or to run the inference. If you go on the Docker Hub, you will find various versions of IBM Watson machine learning. If you just search Power AI on the Docker Hub, you will find those versions right now. We are packaging either containers with all the packages or containers only for TensorFlow, PyTorch with various support. So until 1.6, we're supporting Python 2.7 as well. But moving forward with 1.7.0, we have only the Python 3.6 and 3.7 support into the Watson Machine Learning Community Edition. So all these things are available there. You can just check them and consume them. As we go more and more on the Kubernetes and OpenShift, we see a huge demand from the security departments to validate those containers, to keep them alive, to have them simple running, and we have moved as well part of those containers as UBI universal-based images into the Red Hat catalogs. Therefore, we can consume them from the OpenShift cluster, and we're going to continue to do this. That's a choice as well for the users that they use, for example, OpenShift systems. I was mentioning that TensorFlow, this is a test our team has done in one of our centers here in Montpellier with Cityscape, where they were able to run the DeepLab version 3 for image segmentation with using 10 times more bigger images in resolution than they could do it with the same GPU by just enable the large model support. So, for example, large model support, what that means is that during the training, so the backward propagation, we accumulate weights, and some of the weights we don't use them. So we send them to the GPU, from the GPU to the one that we don't use them to the system memory via this GPU to CPU NVLink connectivity. So therefore throughput, and it's faster. And we make more space for the data into the GPU memory, right? And this is a continuous process which is happening automatically there, and therefore we can process higher resolution images. It's not only available for automotive, but as well we see applicability of this as well in the aerospace and satellite images. So again, this is something that we have seen and measure, and we have seen some examples here in terms of training time for those high resolution with swapping. So we swap the tensors from the GPU memory to the host memory in the continuous way. And obviously, the example here on the PCIe is very simple because you have more bandwidth on the NVLink CPU to the GPU compared with the PCIe, either is Gen 3 or Gen 4. All right, so a couple of use cases right now, and then I will finish. Here's an example from ZF where they use another product from IBM called IBM Aspera to manage a vast amount of video files, right? So whenever you want to search for a corner case, whenever, let's say, you deploy a model into a car and that car you see consistent, after you deploy it on the car, you see consistent failure for a particular object detection. The question is how fast you can fix that. In the moment you find out, and the moment you have a green line to repair that until the moment you can put that into the car, how fast you can go back, search to your data sets, videos, find those corner cases, take the videos from there, extract what you need, do the annotation, and then push that in the training and so on and so forth. And the key here is this IBM AREMA product that is actually handle this kind of image data sets in a consistent way with the metadata. Another thing it's here as well with AREMA, it's Robert Bosch, you may work with them probably as well, where they they use IBM AREMA as well for the video management, content management, and so on and so forth. So the same things applying there as well. And at the end, it's just operation efficiency and cost reduction. Another thing here, it's another supplier in Europe where they use NVIDIA DGX1 and they use IBM Elastic Storage Server, so ESS 3000 for a huge installation, and the installation there is based on Kubeflow and integration at the container level and so on with IBM Spectrum Scale, which is sitting on the top of the Elastic Storage Server. Another thing, it's Volkswagen AG as well. They use OpenShift inside to accelerate the development of the machine learning and deep learning. In this case, they do as well virtual travel assistant 4.2 ACC and entertainment as well. You can find it on the Red Hat Summit. I think they have the keynote there recorded. So you can see that by just moving to this kind of approach of containerized environment in data center, they can really empower people to do much faster the development. And at the end, the time to the product, it's faster. This is another project where I've been as well involved. It's called Mayflower Project, where we created together with an organization called Promare to be sent from US to UK, to pass the Atlantic. And here we work with the Power Vision just to do the labeling and the training of the models that we deploy them on the edge equipments inside of this ship. So that's very interesting to see this, and hopefully we'll see good results by December this year of how this ship will just go. But again, here it was like similar to what's happening in the automotive, but you need to have taking consideration different kind of issues which happening on the Atlantic. A very interesting project where I've been involved successfully so far. Right, I'm conscious on the time, and therefore I'm open for any kind of questions or remarks.
Thank you, sir. Thank you for sharing your valuable inputs. Any questions for the presenter, participants?
Yes, Mr. Florin, this is Ganesh. Thank you for your presentation. It was more kind of in detailed presentation regarding the back-end process of the AI development towards automobile. My question is, see, your presentation mostly covered upon the research work that is done in the back-end, which we are very less familiar to. Can you brief about the systems that are used in the ADAS, advanced driver assistance systems, through which AI-driven data manipulated or outputs? Lastly, you mentioned a few examples of the client systems. Can you just elaborate or briefly give 2 or 3 examples where it is being actually used in the automobile?
Right. So I can say, for example, for the ProMare, in terms of the devices, we use NVIDIA Jetson TX2, but we move to AGX right now in a particular form. We have seen a couple of issues here. The first thing is that when you train those models and you test them into your data center, that's one thing. But when you try to put them in those devices where the problem that you have is just the power consumption and the power you can give them, not only for consumption and to run, but as well the heating, it's a problem. You need to do the quantization and the pruning of those models. And when you do that, there are various constraints. First of all, because in those devices, you cannot run a single model. They are powerful. So you need to run, for example, one model that can do object detection, one can do classification, another one can do segmentation, and then you need to collect the inference results in the same device or in another device, and therefore need to connect 2 or 3 devices together to take a decision. We call it post-inference. I don't know how you call that one. And when you do this, you have some issues on time synchronization and on tracking all those things together. And when you add another dimension, which is happening in automotive, is that you need to be sure that the system is reliable, and therefore you need to have redundancy by nature. This is another level of abstraction. So we have seen more problems coming from this part on how we offer the post-inference process and how we do you ensure about the redundancy, rather than how better is your model to detect an object or to do the classification or semantic segmentation. Yeah, this is what I have seen so far, where I've been involved. Another thing I can mention here, another customer, I cannot mention his name, but it was about how you test those models before put them into a car, right? So we are working to with the Carla. I know if you are familiar with that. This is software for simulation, and we had the need to interact between, for example, a model that you created and is running, for example, on an edge device, and how you integrate that further with the simulation environment, like like a game, or in this case it was Carla that was rendering scene and so on and so forth, before to deploy that model. And that process is very painful, because rendering of the scenes for a particular environment, it's taking a lot of time. Typically, it's based on the Unreal Engine. Majority of the vendors that they have, even I think NVIDIA has a software a solution called Drive Constellation. It's like a DGX1, but similar, created special for the simulation. So we see people struggling with that part of the validation of those models before they can send it out and push that into the car. They, not only because they don't know what to do, they know exactly what to do, but in the way that they can automate that process. Because typically it's going in a different infrastructure, different kind of devices. Another thing is the problem we have seen, particularly what I was involved in, how you can change the firmware of that hardware. So for example, if you take a DrivePX board, the question is how fast you can change the firmware, right? And that is it's a problem because firmware is, you cannot put it over the air. And it's very, it's a very serious process when you change that. And therefore we have seen some companies where they're trying to build their own hardware solution just to avoid those kind of things, right? They don't like to have to take this default action of, changing the firmware being a very hard thing. You need to bring the car into the workshop and so on and so forth. So I don't see it's only one challenge. We have seen various challenges in many places. Another example I can give, and I will just stop with this. For in-cockpit AI, we were discussing with a company. They are trying to shrink the training from 220 days to 8 hours. And we say, okay, sure, we can give you a big cluster and so on and so forth. But we found out by doing this that they were having custom kernels to do, let's say, int8 training, and just trying to move this kind of kernels into a kind of Volta GPUs from NVIDIA 1080 Ti cards. It was tremendous work, and they were not willing to do it. And interesting was that work was not documented. So various issues. Whenever you want to push something into the edge, into the car, you need to refer to power consumption, heating problems, and therefore you go to 8-bit precision, 4-bit precision. And therefore that's why I show you as well the inference chips that we are working. Problems with the weight is still there. You always, whenever you start the car, you need to load the weights in your edge systems, in your computers that you choose, or FPGAs in this case, and so on and so forth. So we see problems around that, and obviously about the consistency of the predictions.
Thank you, Mr. Florin, for the explanation. We could at least basically understand the difficulties in that part. I just have one more question. Can you just give us few examples, one or two, AI systems that have been successful and implemented in automobile? Just like object prediction and alerting the driver, just like that. Are there any other AI systems that have been successful and implemented in automobiles?
So as IBM, we are not directly involved in this. We just supply the technology for it, right? But we are in some of successful projects that you see it on the roads, like Tesla, involved with our technology, for example, right? Is not in the car, but in the backend. In the car, I think we are in Asia, in one of the leading car manufacturers there for the quantization and pruning. So IBM Research had a work there on just reducing the precision and try to preserve and by reducing the precision, try to preserve the accuracy of the model, because whenever you reduce the precision, you lose some accuracy, and there are ways to do that. So we were involved in that particular case. Other successful, I think, depends on the level of autonomy, right? So if you look on the level 1, level 2, I think it's everywhere right now. They have lane detection in the cameras. For example, here Bosch, I will give an example. They have created a camera that any car supplier can take that camera, and they have some basic things like lane detection, pedestrian detection, and so on and so forth. And it's based on a custom board that has some ARM chips inside with an FPGA, I think like something like Zing series 8000. So there are various things. Either you use a car manufacturer or you use a part suppliers. We see more and more of those traits, or they try to give various parts. The question is how you can integrate them and how you can monitor them when you try to assemble the car.
Thank you, Mr. Florin.
Thank you, Ganesh. Thank you, sir. Any other questions to the presenter?
Mr. Florin, this is Hari. I have 3 questions, if you can answer them in a list. Like number 1 would be regarding autonomous vehicles. we have been looking into first generations, they were looking into lidar based systems, and nowadays they are moving into completely vision based system. Do you find anything disadvantages in lidar based system? And
yes, I can give you the first question, the first answer on this. First of all, on the LiDAR you have two main issues. Is the way there are not so many tools whenever it's about annotation of the pointing cloud data sets. So it's, as well, the knowledge and the models are not, people they don't develop so much around because this technology is expensive. And second, when you use a LiDAR, for example, on a car, and the car is seeing a tunnel, it's like the LiDAR would say that's a wall, right? So, and this is something I know from researchers from one of the European company providing this kind of technology. So with LiDAR, there are various advantages, but at the same time, in reality, there are many disadvantages coming from price, coming from this use case with LiDAR and the tunnel as a corner case, and therefore, when you think that you want to sell a car, and let's say the price of a car you want to sell is around $10,000, and you put technology for autonomous driving inside, which is another $8,000. How many people they will afford to buy that for the use case that you want? So the technology has to be cheap enough that people will accept that. And so far, we have seen that the sensors from cameras are the most cheapest and successful.
that's good, sir. But I think, but I'm not sure whether lidar is anyway more accurate than vision system or not. Even if it is costly, is it a better accuracy than a vision based system?
If you consider that on various weather conditions, like snow and so on, yes, will be right. That's very clear. But if you consider that, for example, in things like like a tunnel and so on, there is a risk there. So it really depends on the implementation on how you do that. Personally, I'm more for cameras-based autonomous driving assistance rather than combining radar with LiDAR and so on, because that you cannot have only LiDAR, right? You can have cameras, radar, or cameras, LiDAR, or only cameras. Whenever you add another type of sensor, for example, let's take sound, for example, right? It's very simple. So whenever you want to have sound, like to detect when the road has water, right, or a sleepy road, you need to do fusion. Handling two sensors and inference coming from two sensors in the same time, there is a challenge. And I've seen various companies trying, like, for example, Valeo has an interesting concept on sensor fusion, right? So it needs a different kind of neural network architecture to deal with that, right? Rather than just take the individual facts. So I don't believe there is an answer. It's more like how you feed those things together, how you feed those sensors together. If LiDAR is solving something for you in a particular environment, yes. But don't forget that the industry right now is trying to take, for example, those HD map, high definition maps as well, which is giving you a big precision, right? So the LiDAR will really help you either for very bad weather conditions, or in my perspective, or for path planning in terms of object detection. So how long is the distance, right? And you have seen as well implementation with stereo cameras, probably, where the accuracy is pretty good, right? So I personally I believe LiDAR is very good technology, but the way you need to implement that and the way to maintain that and to make it work with other sensors is creating it's creating a lot of challenges from that perspective.
More about the bats and dolphins, they have extra sensors, right?
Yeah.
Okay, the next question that I would like to post you to is, what would happen if at all the cloud internet service as well as GPS is somehow disturbed? Assume we have an internet outage. what would happen to these autonomous vehicles? Will they be able to run continuously, or will they scramble up?
So it depends on the way you implement this. For example, if you have, let's say, the models running there into the devices and so on, they will be able to have some sort of autonomy, right? But if you build some models that they will take some weather condition, weather patterns, and so on and so forth, and that is embedded. And if you don't have them, the systems, you design the system to deactivate the autopilot, or let's say the autonomy, right? I don't want to mention autopilot, the autonomy from that. Then obviously they will not be able to work, right? If you design a system just to, for example, detect the lane, keep the steering, detect the objects, break the system in case that there is an object in the front, start, and they will be able to avoid, to do actually collision avoidance, right? Because navigation means by nature satellite communication, right? It means position. You need to have the position. Either you use satellites from Russia, GLONASS, from US, or other kind of satellites. For example, in Europe, we're trying to do it Copernicus here to have this. You will not having satellite communication, not having GSM or 5G communication means that you are off the grid. And therefore, the only thing you can do is just collision avoidance. It's like you drive, you take a car, and you don't have any map into a city, and you have to go from point A to point B. You cannot in a large city.
Human intervention, I guess.
Yes.
And have you been to India, sir?
No, I've been up to China.
So
fly
in
over
India,
to India. Yeah.
Well, okay. In India, we don't have much sophisticated highways, as you may have displayed in your slides, right? The speed limits or directions or the signboards. We don't have so much. So how do you think future for AI-based autonomous vehicles in India?
Well, that's a very tough question. So I've never been there. So I just seen movies and discussed with people that have been there. But in my view, you know, it's like people to people, right? So whenever you are in a crowd with a person, you just don't bump to a person, right? So you realize that someone near you and you're trying to find a way to move around that. And if that happened, let's consider something like Bluetooth beacon, right? So whenever you have, let's say, cars that they can emit, in my view, right? They can emit something like a signal. That signal can be picked up by the cars around. You can say, well, around that car at this speed, this is my speed limit, 2 meters, 3 meters. And have an algorithm, in my view, that can take that into consideration, that can take over the steering wheel and brakes and acceleration by just not having, that I think can be something which goes to something called connected cars. The question is how you integrate that. You integrate that via 5G, 3G, and so on, or integrate that by a specific industry standard that will appear in the future, where a car coming close to a car can emit a specific radius sound or radio sensor or a radio wave that can be perceived by the other car, and they can have a collective decision. That's my view.
Well, sir, thank you, sir. Venkat, sir? Hello, Venkat, sir?
Thank you, Hari. Thank you. Thank you, sir, for sharing valuable your experience. And any more questions, presenter? If no more questions, I have shared the feedback survey link in the chat box to all. Kindly complete the survey, take the survey, and input your ID number and rate the session for today. So if any other feedback about the training, about the learning you have during this training, you can type it in the chat box. Thank you, Mr. Florin, for sharing your valuable experience with us. And I think most of the examples you have shared, it was very useful for us for apply in our domain here. And Mr. Ganesan, I request you, you can add something at the end. Mr. Ganesan, are you there, sir? Okay, I request all the participants to complete the feedback survey link, which I have shared in the chat box. This input will be taken for our future designing of the program and also for your attendance record. Mr. Florin, do you want to add something else at the end, sir?
Yeah, thank you very much, first of all, for participation. One thing I want to mention, this was an overview just on what we do on various parts with various products, right? So this field of transformation of the way the industry goes right now from the thermic engines to electric engines, because that's something that will happen everywhere sooner or later, it's giving us an opportunity to rethink the way the cars are, not only for the way they drive, but as well the way we supply the software inside. So that's something said. What I presented here was just an idea of what we do so far in various places, but we have various as well, other kind of innovations in various places in the way we do crash simulations and so on and so forth. We are living right now we are just stepping up into new years where for autonomous industry and for car industry would have to transform to continue surviving. Either we are speaking about trains, buses, and so on and so forth. So I think for everyone here, we have to understand that there is hundreds and thousands of opportunities to present, come with new ideas, and moving forward. So thank you very much for participating. I hope this was a good overview on what we do in some directions. And if you have more specific things in the future, just please contact us and see how we can go forward. Thank you.
Thank you, Mr. Florin, sir. I hope we will plan further more sessions with you in the future.
Your voice is not audible.
Yeah.
Okay. Thank you, Mr. Florin. Soon we will see. Hope to see you